We'll start our detailed analysis of shock waves by looking at what happens to a gas when it passes through a normal shock wave. An important assumption that we'll make in this section of the course is that shock waves are discontinuities in the flow. We'll look at the gas upstream of the shock wave and the gas downstream of the shock wave and find that the gas properties will be different. In our analysis, we'll not take into account how the properties change through the shock wave, but we'll conserve mass, momentum and energy and make a few more assumptions about the gas to find the conditions downstream of the shock. We'll assume that the gas on either side of a shock wave is a continuum and that the properties of the gas change instantaneously as it passes through a shock wave. This is an approximation, but a very good one in many situations. In this video, I want to look at why we can make such an assumption and situations where we can't make that assumption. A gas actually consists of a combination of atoms and/or molecules. Let's just refer to them as particles for now to keep it simple. If the temperature is above absolute zero, then the particles will all be flying around at some finite speed. Here's an animation of the motion of many particles, representing particles in a gas. Their speeds and directions are all different, but their mean speed depends on the translational temperature of the gas. Particles are continually colliding with other particles. After each collision between two particles, they'll both change their speed and direction because of the collision. We'll see in the section on hypersonics that if there are molecules in the gas and they're travelling at high enough speeds when they collide, the collisions can excite vibration and rotation of the molecules, or the molecules may dissociate into their constituent atoms. At higher energies still, the gas may ionise. We refer to these as high temperature or real gas effects. But more of that later in the section on hypersonics. In our initial analysis, we're going to ignore those high temperature effects and treat the gas as what is referred to as a calorically perfect gas. This means that the specific heats of the gas remain constant as the temperature and pressure change. And the perfect gas relationship, P equals rho RT, holds. Let's go back to the particles in the gas that are all colliding with one another. The reason I want you to think about this now is because the thickness of a shock wave depends on how frequently these collisions are occurring. Let's think about one individual particle in the gas. As it moves through this cloud of particles, it will eventually collide with another gas particle. After the collision, it will have a new speed and direction and will stay on that path until it has another collision. We define a parameter called the mean free path of a gas as the average distance that a particle in the gas will travel before it collides with another particle. So let's look at one particular particle in the gas and track its path. You can see that this particle travels a certain distance before it collides with another particle, and then travels another distance in another direction until its next collision. And the process continues, with the particle travelling in a straight line between collisions. If we were to measure the distance the particle travels between collisions, the straight sections of the path here, and take an average of all those lengths, we would have the mean free path of the gas. The thickness of a shock wave is typically of the order of only a few mean free path lengths of the gas. In air at ambient temperature and pressure, the mean free path is of the order of 100 nanometers. That's of the order of 10 to the minus 7 meters. So, shock waves in air at such conditions would have a thickness of that order, so only a fraction of a micrometer thick. Therefore, treating a shock wave as an instantaneous change in gas properties is a good approximation for air at such conditions for vehicles of typical size. One time when shock waves can't be treated as being very thin is when we are dealing with shock waves in the air at very high altitudes, altitudes near the edge of the atmosphere. At high altitudes, the density of the air gets very low. Then the distance a particle in a gas will travel between collisions gets larger, and therefore the mean free path of the gas increases. We call the analysis of this type of flow rarefied gas dynamics. In rarefied flow, we usually can't make the assumption that the shock waves are very thin compared with the characteristic length of our vehicle. In hypersonics, we can encounter rarefied flows. For example, spacecraft re-entering the Earth's atmosphere will encounter rarefied flows when they first enter the atmosphere. As they continue to lower altitudes and encounter air at higher densities, our model of a very thin shock waves is a good one. Next, we'll analyse the flow of a gas as it's processed by a normal shock wave.